Okay, so here is problem 40 from chapter 34. The figure below shows a 5-turn, 1 centimeter diameter coil with radius with resistance 0.1 ohms inside a 2 centimeter diameter solenoid. The solenoid is 8 centimeters long, has 120 turns, and carries the current shown in the graph right here. A positive current is clockwise when seen from the left, so that's this right here. And they want us to determine the current in the coil at time 0.01 seconds. So that's right here, 0.01 seconds. Okay, so using Faraday's law, we know that current in a coil, is the induced EMF divided by the resistance. This is Ohm's law, but we use Faraday's law to find the induced EMF. And that's what this is right here. So yeah, we use Faraday's law to get the induced EMF. Plug that into this equation. And then to find the flux of the coil, we know that it's the dot product of the area vector and the magnetic field vector. And we're finding the flux of the coil, and so we're assuming that the flux is enclosed in the coil, so that the area vector would be pi r squared times the magnetic field of the coil, and that's what this is. Biot-Savart law times cosine 0. And so then you plug that into this equation and you get this. And then you see that these are constants. You just pull them out, and then you're left with the derivative of the current inside the solenoid. And you know that that's the slope of this graph. And the slope of this graph is negative 0.5 divided by 0.01, rise over run, and then the absolute value of that is 50 amperes per second. So then you plug that in for that, and then you're given all this other information, and then you get 0.37 milliamps, which is the current induced in the coil. And because this current in the solenoid is decreasing, as shown by the graph, that means the magnetic field that's going to the right through the solenoid is decreasing. And according to Lenz's law, according to Lenz's law, there's a magnetic field that's induced going the opposite direction. So this is decreasing, so it's going that way. So the induced magnetic field is going this way. And using the right-hand rule, we can figure out that the current in the coil is clockwise when seen from the left. So it is positive 0.37 milliamps.